We're going to provide you with a brief outline for your test that comes up on Wednesday on simple harmonic motion of waves. I'm going to break this outline down into two separate sections. First one, simple harmonic motion. Second section is on waves. Now, it's been a little while since we've done the simple harmonic motion portion. Hopefully it comes back to you pretty quickly. Okay, we started off simple harmonic motion with a definition of simple harmonic motion, what it really means. Okay, it means, we think of it as motion that repeats itself, but what it really means is motion in which the restoring force is proportional to the displacement. And that's really just Hooke's law, right? If the restoring force is proportional to the displacement, then F is equal to K times X. I'm going to put in brackets here, F is equal to negative Kx as well, because although Kx represents the applied force on the spring relative to the displacement, which is really just the definition of simple harmonic motion, Hooke's law technically involves the restoring force, meaning negative Kx. If on a test you use the wrong one and make it positive Kx when it should be negative or vice versa, it's not the end of the world. You're still going to get the same value and I'll probably mark it right. Remember that the stiffer the spring is, the higher the spring constant. And remember that X stands for the displacement, not how far a spring or elastic has moved, but how far it's stretched or compressed. In the assignment that you guys had due today, I think in question number 7, I want to say it was, question number 7, maybe question number 8, you had a spring that was compressed 5 centimeters. X would have been 5 centimeters, although you want to convert that to meters. So if you happen to be given a question where you're told, I don't know, maybe we throw this in as a trick sometime, where you're told the spring is moving 10 meters, but at the time it's moving 10 meters, it's compressed 5 centimeters, then X would be 5 centimeters. Delta D would be the 10 meters. Now, sometimes we need to find X. Sometimes we don't have the value of X, so we got to find it. And when we do, we often end up using our spring or elastic potential energy equation, which looks like this. EP is equal to 1/2 kx squared. So you might have to find K using elastic potential energy, or you might have to find K using Hooke's law to plug into the elastic potential energy. These two equations often go together. F is equal to Kx, and EP is equal to 1/2 kx squared. So these two spring constants, of course, end up meaning exactly the same thing, and they go back and forth between one another. The units for elastic potential energy, of course, are joules, just like the units for any other kind of energy are joules, and we're talking about potential energy being a scalar. Okay? All kinds of energy are scalars as well. Well, then we went to conservation of energy with springs. In other words, this is where we had the spring doing something, not just the spring being compressed, what's its potential energy, what's its force, whatever, but it's doing something. Like it's causing something to speed up or to slow down or whatever the case may be. When a spring causes something to speed up or slow down, then we're probably going to say EI equals EF. Now, EI, it could be one of 3 types of energy or a combination of those 3 types of energies. We've got I'm not saying necessarily that it's always all 3 of these, but we can choose from 1/2 mv squared. Maybe it's moving initially. Maybe it's got a height initially, so we say mgh. And maybe the spring is compressed or stretched, so we'd say 1/2 kx squared. Generally, these two will go together. Sometimes you have a height and sometimes you have a speed. And these two will go together. Sometimes you have a height and sometimes you'll have a spring that's compressed or stretched. Generally, the first one and the last one don't go together. So if you've got a spring at the top of a hill, then you're going to have spring potential and gravitational potential. If you've got a spring at the bottom of a hill, then you're probably going to have kinetic energy and spring potential. But generally, kinetic energy and spring potential aren't going to go together, either for EI or for EF. When you get one of those questions, then you can be relatively confident you're going to get one, right? We saw one of those on our practice test. We did a few of them in class. When you get one of those questions, look at the situation, and for your beginning and your end, wherever you choose your beginning and end to be, you ask yourself, first of all, do I have a spring that's compressed or stretched? If the answer is no, then forget about spring potential. If the answer is yes, then you got to put in 1 half kx squared. Is there a height? And when the spring is compressed, if there is one, is it moving? If the answer is no, then there's no kinetic. If the answer is yes, then there's kinetic energy. We talked about the pendulum as an example of simple harmonic motion, or at least a very, very good approximation of simple harmonic motion. We learned about the period of the pendulum, and period of the pendulum was t is equal to 2 pi square root L over G. We had to be able to rearrange that, though. How do we rearrange it? Well, the 2 pi goes down by dividing, square root it, multiply it by G to get L. So if you're solving for L, it becomes T over 2 pi squared times G. If you're solving for G, you're going to take T over 2 pi squared but down by dividing. And it's going to look like this. And then, of course, we know that we could find the frequency of this pendulum using one of the equations we learned in our last unit. Okay, we know that frequency is 1 over the period. So you get the period here, we can solve for the frequency. Or given the frequency, we could get the period and then solve for something else, right? Maybe it talks about the frequency of the pendulum is this value. Here's gravity, what's the length of the pendulum? Get period and then solve for the length of the pendulum. And finally, within simple harmonic motion, we talked about resonance. We defined a couple of terms there. First one was resonance. Definition, and we also talked about resonant frequency, which, as you know, became pretty important later on in our unit of waves. Resonant frequency and resonance. What you had your quiz on today, this whole standing wave thing. Resonant frequency, remember, is the natural frequency at which something wants to vibrate. When you hit the wall with your hand, it makes a sound. And it's because the wall has a particular resonant frequency at which it wants to vibrate. When you pluck a guitar string, it makes a sound because it has a certain resonant frequency at which it wants to vibrate. When you start stomping on the pedestrian bridge down by the library, it starts vibrating back and forth because it has a resonant frequency at which it wants to vibrate. If we apply a force at the right frequency, at the resonant frequency, the resonant frequency is now, 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 and we apply a force now, 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 then we can cause the vibration to grow, the amplitude of the vibration to grow. That's resonance. Okay, resonant frequency is the natural frequency. Resonance is when the amplitude of the vibration grows because we're applying a force at the right frequency, at the right rate. It's the opera singer, right? The resonant frequency of the glass is, I don't know, 800 hertz, we'll say. I have no idea what it is. Okay, but let's say it's 800 hertz. The opera singer sings at 600 hertz. Okay, it's just annoying. Okay, the opera singer sings at 800 hertz. It becomes entertaining because all of a sudden now the glass is going to start vibrating because she's applying a force at the natural frequency of the glass. Maybe she breaks the glass if there's enough force there. All right. And then we went to waves, and we talked about, first of all, the relationship between simple harmonic motion and waves, in that wave motion really is just simple harmonic motion, but it's simple harmonic motion of a whole bunch of particles. It's a simple harmonic motion of all the particles within the wave. We had our transverse wave where the particles are vibrating back and forth like this in simple harmonic motion, and we had our longitudinal wave where the particles are vibrating back and forth like this in simple harmonic motion. Each of those particles stay within their own little area, but they are going back and forth, motion that repeats itself, motion which the restoring force is proportional to the displacement. They're going back and forth in simple harmonic motion. Know what the difference between a transverse wave and a longitudinal wave, which way the particles go, but also be able to label things like wavelength, crest, trough, compression, rarefaction, all the stuff that go with the pictures of transverse and longitudinal waves. I'll tell you what, the biggest mistake that people probably make on this is the amplitude. The amplitude is the size of the wave measured from the equilibrium position to a crest or to a trough. Okay, what do people want to do? They want to go from the top of a crest to the bottom of a trough. That's wrong. Okay, it's from the top to the equilibrium, or it's from the bottom to the equilibrium. We talked about the speed of waves. You guys had a question on your assignment that you just handed in to me a few minutes ago on the speed of waves. Okay, we know that we can use basically a couple equations for this. V is equal to delta D over delta T, and V is equal to F times lambda. Although, of course, we know that we can also use F is equal to 1 over T if necessary. Use these equations in conjunction with each other. But just make sure that when you use them, make sure you've got the right time and the right distance. What you often find in these ones, I'm going to write a little note here about this. What you often find in these ones is the end up having to divide or multiply by 2. Okay? If you're given the distance from you to the wall, but you want to find the time that it takes for sound to go from you, reflect off of the wall, and then back to you, then whatever time you get, you got to multiply that by 2, or multiply the distance by 2. Okay, if we're given the time that it takes for sound to reflect off of a cliff and come back to you, to echo back to you, but we want to find the distance from you to the cliff, then we got to divide the time or the distance by 2. So remember that sometimes, not always, remember to sometimes multiply or divide by 2. It'll always be that the time or the distance that you're going to do that to. Talked about waves at boundaries. There's basically 2 situations that we can encounter there with waves at boundaries. The first one, well, 2 general situations. The first one is when the waves are very similar and we get transmission. And the second one is when the waves are very, very different and we get reflection. The reality is we always get a little bit of both. The wave that's transmitted, you might remember one thing always remains the same, everything else changes, right? What stays the same? What is it that doesn't change ever? Once a wave has been made, this always stays the same. Right. So know the effect of transmission on frequency. It stays the same. Speed, wavelength, direction change. So remember that frequency stays the same. Remember that speed, wavelength, and direction will change. When we have reflection, there's a couple of things that can happen within reflection. The part of the wave that's reflected will either reflect right side up, or on the same side as it went down on, or it will reflect inverted. Remember when it's reflected right side up and when it's reflected inverted. You know that you get a question like this, it's not going to be a written question, it's going to be a multiple choice question, right? This is what lots of you guys struggle with, is the multiple choice questions. So pay attention to little details like that. When the wave encounters a boundary that's more dense, or when it encounters a boundary that it's attached to, it's going to be reflected right or upside down. If it encounters a boundary that's less dense or that it's not attached to, then it's going to be reflected right side up. So again, little details like that are what get us those, those couple extra points on our multiple choice that, that maybe we are struggling a little bit with. And then, of course, we also have that law of reflection, which comes into play when the wave hits the boundary at an angle as opposed to straight on. When it hits at an angle, then you know that it's going to bounce off at the same angle. The angle of incidence equals the angle of reflection. Either right side up or upside down. Okay, the first part that we learned here, the upside down, right side up thing, it doesn't change. It's just that now it reflects off at an angle, same angle as it struck it at. Talked about interference and the superposition principle. Had one of these on your assignment as well. This is when you have two waves. And you want to find out what the interference pattern looks like. It's this spot that we care about really, where they're overlapping. Because we know in this spot, it's not going to change, right? But in this spot in the middle there, we've got to add up how much above, how much below the waves are. Add them up. Here we get destructive interference because we've got crest and a trough. Here we'd also get destructive interference because we have a crest and a trough. If we have constructive interference, even in one small section, then one small section is going to undergo destructive interference if you have a crest and a trough. Sorry, these are both destructive. What did I say? These are both destructive interference because they're both crests and troughs. But if I have two crests, even in a small section, that small section will have constructive interference. Two crests or two troughs give me constructive. We talked about diffraction in interference. Diffraction, remember, was the spreading out of a wave. Remember what it is. Remember the effect of the size of the opening. The effect of frequency and wavelength on it as well. The smaller the opening, the more diffraction you get. The smaller the frequency, the more diffraction you get. The smaller the wavelength, the less diffraction you get. If you don't remember the whole frequency thing, okay, again, think of the story that I told you about AM radio versus FM radio. AM is smaller frequency, I can hear it at the bottom of the hill. FM radio, bigger frequency, I can't hear it at the bottom of the hill. Smaller frequencies must diffract more. And also remember that interference pattern that you saw when you had two diffracted waves, right, like this. Remember those lines, those areas, those lines of constructive and destructive interference? We call them nodal lines or antinodal lines. The nodal lines, constructive interference, guy sitting on an air mattress. Sorry, nodal lines, destructive interference. Guy sitting on an air mattress, it's calm, water's calm. But we have an antinodal line, constructive interference. You're bobbing up and down like crazy because the crest and the troughs are both twice as big. Then we talked about standing waves, which is what you just wrote your quiz on today. I think you guys are doing okay with those. Okay, remember the difference between an open air column and a closed air column? Either remember or derive the equations because they don't appear on your data sheet. Remember or derive them. And remember what we focused on a lot last week. You're always going through the fundamental. So if you're looking for the frequency of the third harmonic, then get the frequency of the first one. And if you're looking for the frequency of the second harmonic, when you've got the third one, then get the frequency of the first one and then multiply it by 2. Always go through the first harmonic and then multiply it by 2 or 3 or whatever the case may be to get the one that you want. Always go through F1. And also remember the last thing. Remember when there's even and odd harmonics. So even versus odd harmonics. You always have the odds. You always have the first, the third, the fifth, the seventh, and so on. But when you have an open air column or a string, then you also have evens. But when you have a closed air column, like you had on your quiz today, there are no even harmonics. So if you ask for the first two harmonics experienced, it would be the first and the third, not the first and the second. But if it's an open air column, the first two harmonics experienced would be the first and the second. And finally, the Doppler effect. Obviously, we had an equation here. FD is equal to VW over VW plus or minus VS times FS. Remember the variables. Okay, the D versus the S, what that means. The W versus the S, what that means. And then here's the big thing right here, the plus and minus. It's going to be VW minus VS if they're approaching each other. And it's going to be VW plus VS if they're receding. So if the fire truck is going away from you on the side of the highway, then it's going to be a positive value. If it's coming towards you, it's going to be negative. Be able to rearrange for FS here. You had a question in your I think you had a question in your check and reflect questions that had solving for, I think it was VS or VW. I think it was VS you're solving for. But honestly, on a test, I'm likely to ask you to solve for either FD or FS, because that's pretty ugly to rearrange for VS.